Alright. If you can hear me, say something in the chat, because I don't know what's going on. It's bugging out on me again. Say something about you can hear me in the chat, and we'll get this show on the road. Okay, I'm gonna start closing things on my computer. I said I would do it before, but I never did. I'm pretty sure Skype is destroying my, everything. Okay, cool. Oh, you guys can hear. Oh, this is nuts. Okay. Okay, so the first thing that we're asked to do in this problem is come up with the first degree. So we know yes, I'm back. I'm back, and it's working, and I think we're good. And I'm sorry, my computer is just having an absolute load of issues. And if you were here at the beginning, I totally warned you. The thing's kind of a piece of trash. Yes, I'm alive. I'm alive, Manny. If it's not live, please tell whoever's watching to refresh. Darn, I lost all my likes on this video. Where'd they all go? What in the world? They all poofed away. Damn it, Ferguson. That's awfully rude. Okay. So, I can't, get... Is that still visible when I'm all the way out here? Can you still read what those numbers are? Okay, so for part A, here we go. This is it. This is the final actual explanation and answer for everything. So we know that when we're writing our first degree, the first degree Taylor polynomial that we're writing is about A. So we know that when we're following the format of a when we're following the format of a Taylor polynomial, we know that we're going to have just the again, I'm gonna write that general formula here. The general formula for a Taylor series, the general format that you're following, it's a sum from n equals 0 to infinity, or a series rather, over, it's going to be the nth derivative of A over n factorial times x minus A to the n. This is our general formula that we're going to use for everything Taylor series. If we're writing a first degree Taylor polynomial, that means that we're going to take this sum out to 1. So it's basically asking, using these values that we see in the graph, it's just asking us to write out this, except we're going from n equals 0 to 1 of this garbage. So in our case, what that's going to look like is the 0th derivative, or the actual function h, at a. They specify in the problem that they want the first degree polynomial for h about x equals 2. If you guys don't know what a Taylor series is, this is BC. So if you're in Calc AB and you don't know what's going on, just sit tight. I'm going to get through this problem as quickly as I can. So following this format, we're going to take our 0th derivative, h at 2, over 0 factorial times x minus 2 to the 0. That's going to be our n equals 0 term. And we're going to add that to h prime, the first derivative, at 2, over 1 factorial times x minus 2 to the first. So now we're going out. This is the first. It's a if you guys are having trouble going back to the old video, then go to my channel, click on my name, and you can go back to the video that I had before. For some reason they got separated. I'm not exactly sure why that is. Okay. So we're just going to simplify this using the values that we have in the table. So 0 factorial, that'll go to 1. X minus 2 to the 0, that'll go to 1. So this is really just asking for h at 2. So this is going to equal 80 plus, and now this is asking for h prime at 2, which is 128, times x minus 2. So this is our first degree Taylor polynomial, which we can write as P1 of x. Let me get my pink marker. Right, so this here So the next thing that we're asked to do is use that to approximate h at 1.9. So what we're going to do is just straight up plug in 1.9 into that and get 80. (1.9 minus 2 will be negative 0.1. So 67.2 will be the next answer that we get. Following this, we have to determine whether or not this is an overestimate or an underestimate. And what we can do is we can look up at this table. We know, due to the nature of the Taylor series, that if h prime is increasing at the instant that we're taking our approximation, we're going to be underestimating. That's just kind of a rule you can remember. I'll write that down and put that in a little box. That's going to be really important. So that tells us the first thing that we need to know. So, yeah, that does it for part A. Does anybody here still is anybody in this chat still caring about series, or did they all disappear? Okay, alright, cool. Alright. Okay, cool. Just making sure, because it was silent for a second. Okay, so we're gonna do this. Alright. Alright, we'll do a couple series problems then, just for everybody. So now we're gonna write the third degree polynomial. The third degree polynomial is gonna be done in like exactly the same way, except we're just going to go out again. I'm going to write this formula again. We have our function at a over n factorial times x minus a to the n. So now we're writing our third degree Taylor polynomial and approximating h at 1.9 with it. William, yes, it does. It is an it does apply vice versa. If h prime of x is decreasing, it will be an overestimate. This is, I'll add that. And vice versa. Remember that this page will be uploaded to that Google Drive when I'm done at jmag.me/calcreview. Okay, cool. So again, bringing this out to the third degree Taylor polynomial, we're going to have, or not, I guess it'll be, right. So this is the format that you're going to want to follow when you're doing all of these, and you don't necessarily have to simplify.
When are you going tomorrow?
I don't know if I am.
Did you see Wetzel?
Went there. I may or may not, I don't know yet. So just following this format. Emily 1099, no, I'm a high school senior. Okay, so now we're just going to use the values in the table to sort of fill this in. So I can make this work. This is basically going to become, our first two terms are going to stay the same. Gabby, this is not the first part of the review. All the things that say done are in another video. If you click my name, you can go to my channel, look at my uploads, and see the previous things that I've spoken about this evening. I really wish that stream hadn't stopped. That's very frustrating. Oh well. So okay, so we know our first two terms already from part 1. It's going to be 80 plus 128 times x minus 2. So our next one is going to be the second derivative at 2 over 2 factorial. So that'll be the second derivative at 2 is 488 over 3, and that's going to be over 2 factorial. So, oh, this is going to be disgusting. And then the next term will be the third derivative at 2, again, over 3 factorial. So that'll be 4088 over 3 times 1 over 6 times x minus 2 cubed. And so again, you would just use your calculator to approximate, like to plug in 1.9 and approximate that. Does anybody need a more elaborate explanation than that? Or do you want me to? I do not believe so, Redvick. So then you would just plug in 1.9, which according to College Board has it at 67.988. Okay, so we're about to go to Lagrange. I'm going to use the Lagrange error bound for the whole. Okay. Yeah, this is Lagrange error bound time. The Lagrange. Who's roses on roses? I'm not familiar with that. I got a 5 on this when I took it. So explaining Lagrange error bound now. The logic for Lagrange error bound, basically, when we're analyzing the third degree Taylor polynomial to determine, like when we're working with a Lagrange error bound, you have to look at the next degree, like the next derivative of h. So the third Taylor polynomial will go up to the third derivative. So you have to look at the fourth derivative and see whether or not it's increasing on the interval that your function deals with. So like in this problem, they tell us all four derivatives are increasing on the interval 1 to 3 inclusive. So what that tells us is that because it's increasing the entire time, we can look at what the maximum of, like how can I explain this? We can look at the fourth derivative of h and look at the interval between where our estimate is and what x value we're creating our Taylor polynomial about, and seeing what the maximum value of the fourth derivative is on that interval. So if I can explain that better, basically looking at the third degree Taylor polynomial, we look at this 3 and say, okay, we're going to look at the fourth derivative. We're going to look at the interval So in this case, I'm doing Lagrange right now, Daniel. So basically, we're looking at the third degree Taylor polynomial, so we're going to look at the fourth derivative of h. The interval that this corresponds to in this problem is going to be 1.9, 2. And so the question that we're going to ask ourselves is, where is the fourth derivative maximal on this interval? Or more accurately, what is the... Here, hold on. I'm going to link that other video to the people that are confused right now. I'm sorry it got split up, guys. I don't know what happened. I goofed. Is it public? Yeah, it's public. Okay, I added the, it should be in the description of this stream now. I use gaming because it's like a darker thing. It's a darker view. Okay, so we're going to look at where the fourth derivative is maximal on this interval. We're looking at basically 1.9. Because we know that it's increasing over this interval, so we're going to look at the fourth derivative at 2 and see that that's equal to 5/84/9, just according to our chart. So the logic here, just to go over, like to explain one more time. Is it buffering really bad? I can't tell. Thank you guys. I appreciate it. Yeah, okay, so 5/84/9, or the fourth derivative at 2, is going to be the maximum value of the fourth derivative on that interval. So what we're going to look at is the difference between the fourth derivative and our third degree Taylor polynomial estimate, and see if that's below the error bound that they ask for. So what we're going to do is we know for a fact, therefore, I'll use the actual word. So we can say that for sure. So basically, the idea behind this is sort of like the, it's similar to the ratio test, in that we're going to compare our third degree polynomial at 1.9 to something that we know is larger than it. We know it's larger. Like we know that 2.0, or we know that 2 is larger than 1.9, so we're going to plug in our estimate for 2 to prove that our estimate for 1.9 is, because we've already proven that 1.9 is smaller than 2, so now all I have to do is look at 2 and see if that estimate is like within our error bound. So what we're going to look at now is because we know what we're like, the question that we're asking is, are we within, because we know h at 1.9, we know that this is certainly less than this. This is just the next. Are we on board with this? This is just this is what this is. This is the next. This is like that Lagrange error bound formula. Have you guys seen? If it were decreasing, the maximal would be at 1.9. Yeah. If it were decreasing on that interval, the maximum would be at 1.9, and you would just have to do this the other way. So this formula here comes from the Lagrange error bound formula that you basically have to just shove into your brain, which is the if I remember this correctly, it's that. This is just something you're going to need to memorize. So that's this Lagrange error bound formula here. So now all that we're left to do, well, the left side is part of the formula, but like the left side is the difference between our estimate. But we're not actually going to evaluate this side because we don't know the actual function at 1.9. We know our estimate, our third degree polynomial estimate, but we don't know the actual one. We're seeing if it's below it. Because we know that the fourth derivative is maximal at 2 because it's increasing over that interval, that's how we can set up this formula. And if this evaluates, like this right side, because we know this is larger than this. If this is less than our error bound, then like by like, I don't know, basically, I don't even know how to like say, like it's like a transitive inequality. Basically, if this is less than the error bound and this is less than this, then this must also be less than the error bound. That's the, I know it's a little bit wacky. I should probably go over another one. I should do like a multiple choice thing. This isn't just necessarily about divergence though, this is just about error bound. So what I'm going to do is just plug in these values using what we have in the chart, which we already know this one, we wrote that down before. That was 584 over 9. 1.9 minus 2, that'll be, which if you take this, plug that into a calculator. That's looking like and that is definitely less than 3 times 10 to the negative 4. So that's how we know. I know that was a little bit convoluted. I can do another one like it if you want. Just like quickly. Does anybody need more clarification on this, or is that okay? Okay. I'm gonna find a quick. Yeah, I'll do another one quickly just to. All right, you got it here. I'll leave this up while I find one. Unless anybody has one on hand when they were looking earlier, I can just find one. Chill. All right, we're gonna do another. You don't know it's guaranteed to be on the FRK. That's why you study. What a silly question. If anybody sees a Lagrange error-bound problem somewhere, please let me know. I'm trying to find a good one. I can only find one Lagrange error-bound question between like 2007 or 2008 and now. So I don't know if that means there's like a low likelihood that it'll be on it, or a high one just because it hasn't been there for so long. Like it's about time that they would add a new one. I don't know. It's kind of spooky. Okay, what do you guys want? If you guys don't have, here's what we're gonna do. To all the people that still need series stuff, if you guys can find a good series problem and you guys can like talk in the chat and agree on one that you want to do, then send that to me on Reddit, and I'll print it out and do it. For now, I'm gonna go back to the Calc AB stuff. We'll come back to the series. I'm gonna move it down in the to-do. I'll keep it still in the to-do. Not gonna move it to done, but I'm gonna move on to logistic growth because people were going absolutely nuts about logistic growth. Is that fair? Fine. You guys agree on one that you want to do. Talk in the chat while I do some Calc AB stuff. Send the one that you want to me on Reddit, and I'll do it. Right now, I'm going to do a logistic growth problem. Okay, I know exactly what logistic growth problem I'm going to do too, so that will speed things up a little bit. I'm going to do, right now for AB, I'm going to do a logistic growth problem. I'm going to print one out from a test. I'm pretty sure it was 2012. Yeah, this is good. It's this is gonna be 2012 number 5. I'm gonna do to anybody that's asking about Taylor series stuff, I'm going to do Taylor series again, but I'm going to do Calc AB stuff right now because people are asking about it. I want you guys to decide in chat what calc problem you want me to do and send it to me on Reddit, and then I'll do it. That's basically how this is gonna work out. If that's cool with you. I'm gonna put the Taylor series stuff that I have right now on the drive. Wait, shoot, I had to copy the problem. Where'd that go? Fuck, I threw that away. Where'd that go? Oh my gosh, it disappeared. It was just in front of me. Okay. Okay. Okay, the Taylor stuff that I have is going on the drive. Stat. Okay, it's scanning right now. Alright. Woo! So, did somebody want 2016 number 1? Is that is that the one you want me to do for logistic growth? Actually, I'm going to do 2004 is good. I'm going to print out 2 things from 2004 because there's a really good logistic problem in 2004. Yeah, this is good. This is so weird. I don't know why they used to do this. Yeah, I'm doing logistic growth right now. Solids of revolution will also include the cross-section stuff as well. I will get that in there too. And that'll be swell. Okay. Alright, it's printing out right now. So you want me to do number 6 as well from that, and that has Lagrange. Okay, cool. Oh yeah, I still have to upload that Taylor thing. Taylor stuff should be up on Drive in just a moment or two. Okay, Taylor and Lagrange 1 are on the Drive now. How many messages do I have? Man, thanks again. If you guys are still here, if that guy that gave me Reddit Gold is still here, thanks again. That's super cool. All right, Lagrange error is on 2008. Okay, cool. So I'm gonna do this logistic growth problem for. I'm gonna do number 5 on this list first, and then we will go back to all that other series gobbledygook. Alright, so I need some of the papers into here. I'm assuming most of the people that are still here are West Coast. Alright, so going over this. Oh, I started writing in. No, it's still blue. I'm just gonna run out of blue ink. Okay, is that? This one is going to be AB and BC. This is logistic differential equations, and that's something that everybody's going to need to know. So the first question is just straight up like, what is the, like, it's telling you what, oh, you guys are all East Coasters, I'm so late. Oh man, poor people. I mean, I'm just going to keep going until people are done. Is probably what I'm going to do. I am East Coast. Yeah, but I don't sleep, Megan. Okay. So, 5A. The logic here. Anything for the 5. Okay. So, we've got P of 0 is 3, and we're wondering what the limit as t goes to infinity of that is. So, hold on. Basically, looking at this equation, what you should absolutely know, just based on differential equations, you should understand the concept of a carrying capacity. As t goes to infinity, regardless of what the initial condition is, this right here tells us that our carrying capacity is 12. So our population, the number of members of our population, as time goes on infinitely, though it is increasing, it's bounded by 12. That's our carrying capacity just by the nature of the differential equation. It's going to be 12 regardless. So, like, the limit in both cases is going to be 12. It's going to be 12 and 12. They will both be 12. Okay, so yes, I'm going to go over that, Rachel. Yes, Wendy, the carrying capacity is based on what's inside the parentheses. So, like, let me see if I can find an illustration. This is 2004, question 5. Is this okay? I think this might just be. I don't remember what a like BC versus AB thing is. Can anybody in BC tell me if this is something that they learned this year as strictly a BC topic? Because I don't remember entirely. It's been 2 years since I've taken. Okay, so this is just BC. Okay, if you're in AB, stop. Like, don't freak out. Okay, cool. Yeah. So basically, the notion. Yeah, this is logistic growth. The notion of a carrying capacity is when basically the population reaches equilibrium. Whatever the denominator is of P, that's going to be your limit as T approaches infinity, regardless of the original capacity. That's like the best I can. I think that's the most it can be simplified. Here, one moment. I'm gonna see if I can math something out to make this a little more. Like, I'm about to do part B. Yes. Okay, so if we're wondering what the maximum population, or when the population grows fastest, based on that initial basic, the idea of logistic growth in a population is that it starts at its initial. It has its initial value when t equals 0, it's going to be accelerating the fastest. The population is going to be growing or shrinking the fastest right directly in the center, based on just like the nature of differential equations. Yeah, half of the carrying capacity. That one guy has it correct. This is kind of a silly question because you're sort of just like answering them. There's not really much logic. It's just you're answering based on the nature of differential equations. This, I guess I'll just put my little like note here. Denominator of P, part B. What we're going to have is Alright, so hopefully part C will have a little bit more math. Alright, is that fine? It's always going to be half of the carrying capacity. Yeah, you would say that the carrying capacity is 12, therefore the population is growing fastest when the population is at half of its carrying capacity, or 6. So for part 3, this is where God, we're going to actually get some math. We're going to turn this into a differential equation, or this is a differential equation, so we're going to separate it. You don't need to justify it. Actually, let me look at their scoring guidelines. the solution provided by The solution provided by College Board literally says, for this logistic differential equation, the carrying capacity is 12. And then it just writes 12 twice. Use the denominator inside of the parentheses, Macaulay. So for part C, this is where we're actually going to get into some math. Work is mandatory, yeah. It's just silly. Yeah, thank you, that one guy. He's correct. Okay, so for part C, this is where we're actually going to get like a... All of the point. Okay, I'm looking right now. All of the points are literally point like A and B. It literally just has a point for an answer, a point for answer, a point for answer. It does not require justification. Yes, that's correct, Clutch. I'll fix that on Josh. Sorry about that. I don't understand why it like separated. It's very frustrating. Okay, I'm gonna make the other one public. Alright, the other video should be public now. Okay, so I'm gonna do part C of this problem. Now this is where we're actually going to have to get into logistic stuff, like actual math, if you will. So we're going to start a different population is functioned by a functioned by a is modeled by a function dy dt equals y over 5 . Okay, so what we're asked to do now is to find y at t. I'm going to continue until, hold on, let me just adjust the title of this video. Alright, I've adjusted the title of the video, so hopefully. Alright, so we're gonna solve this problem. So the first thing that we're going to want to do here is separate the variables, get our dy's with our y's and our t's with our t's or whatever. So we're going to take this y, swap it with that. We'll have dy basically separating those two things. When we integrate this side, obviously we'll get natural log of y equals, on this side we're going to have to do a little bit more work to simplify. Let's actually like turn that into 1/5 minus t over 60, and that becomes much simpler to integrate. So this will become 1/5 t minus t squared over 120 plus c. Remember, we're going to keep the constant on this side because we're taking the derivative of y with respect to t in the original logistic equation, or the differential equation rather. And so from here we're going to need to solve for c. Now that we know our initial condition, we have y at 0 is 3. So can anybody see can you guys see the screen fine? Are we working okay? Hello? Okay, thank you. So now, from here we can say our y is going to be, this constant is going to be pulled out front. So we'll plug in our 3 and our 0. And we're basically going to say 3 equals c e to the, that's all going to go to 0 when we plug in 0 for t. So we can say that c equals 3. Alright, cool. And so now that we're done, we can just say that y, our particular solution, will be y at t equals 3 e to the, actually let me condense this, looks like it'll be t over 5 minus t squared over 120. And that would be our final answer. Yes, you can pull the c down like that. Exactly. That's correct in tense. It's actually really useful. Because all you know is that when you're integrating, there's just a constant there. Alright, so are we good with this? And then the last part is just what's the limit as that approaches infinity, and that's just kind of like the okay. Cool, we good with this? This has been I'm gonna upload this. Should I do this next, or should I do solids? I think I'm gonna do solids of revolution, and then I'll think about doing a series again. All right, so I think I'm gonna do solids of revolution just because I haven't done. Felix, look at the description of this video. To get the rest of the. Look in the description of this video to get the rest of the live stream. Cool. Also the just to wait, hold on. People are. Hold on. Let me scan this and then I'll explain why the limit was 0. Or I'll do it on like the back of a garbage paper. I had a garbage paper. Why my papers keep fucking disappearing on me every 2 seconds? The reason that it was 0, to anybody that's still wondering, if I had my, whatever, it was e to the t over 5 minus t squared to the 120. So when that goes to infinity, this is going to increase faster. This is going to get larger than this. So when we subtract, it's going to become like, it's going to get super small real quick because it's going to be way less than this. This exponent is going to become way less than 0. It's going to very quickly become like 1 over e to the infinity, which is just, or 1 times e to the negative infinity. You know what I mean? Negative 1 times e to the negative infinity. Oh my gosh, it's getting late and I'm talking fast like it's gonna. Ugh. Okay, so this is gonna be. Alright, logistic growth is now in the Google Drive. If anybody needs to review that work I just did, you can get it at jmag.me/calcreview. Alright, cool, sweet, I'm glad this is working. Next we're going to do this solids of revolution problem. Oh, sweet, I did not know that this had... Ritvik, I'm doing it because... I don't know. This is just kind of what I do. Yeah, I'm just helping. That's my thing. I, actually, during the year, like during the classes that I was taking at school, the exam's at 7:40. Yeah, East Coast is still awake. Damn right. What the hell is sleep? During the year, I made these. Those 2 links that I just sent are the things that I did all year in the math classes that I'm in, actually at school. And I don't know, I like teaching. I like doing things. The linear algebra, if you go to the linear algebra link and you go on the chapter 4 cram, that's like my finest piece of work that I've ever done. It's a massive study guide for stuff about linear algebra. It's cool. I just like teaching. I think I might be a TA when I'm in college. It seems like a thing I'd be down to do. But anyways, I should probably get back to doing some calc. This is the thing I was talking about though. Yeah, that's like my favorite thing. Cool, so I am going to do this revolution thing. Alright, so somebody was asking a while ago, I'm a high school senior. I'm graduating in like 2 weeks-ish. And then I'll be in college. I would say my college, but I'm kind of embarrassed. I wish I'd applied somewhere better. I got lazy during the applications process and didn't apply anywhere, and I just kind of, I don't know. I wish I'd gone, I feel like I could have gone somewhere better. Just going to I don't know. The school I'm going to, they have like I'm going there for the programming team. I took Calc AB sophomore year and took Calc BC last year. I took Calc 2-3 last year and took the Calc BC exam. Yeah, damn right I'm rooming with John. Okay, so let's do a solids of revolution problem to get my mind off of college and shit. Yeah, cool. I wish I was going to an Ivy League. Okay, so are these words visible? Because I feel like they're not visible on my screen here, and that means I don't even understand how it would like be visible on your screen. Is it even like? Oh well. Okay, so find the volume when r is rotated about the horizontal line. Y equals -2. Okay, so we have our function. Okay, so we're going to take this figure and rotate it about y equals -2. So what that's going to look like, roughly, is something like this. If we have our... It's going to look something like this. Yeah, this is definitely going to be calculator. What we're going to be doing is, this is the thing we're going to be rotating around down here. So what we're doing is making like we're going to use the washer method for this, because we're revolving around an axis, or like our axis of revolution is 1, not a bound of our curve, and 2, a straight line. So what our washers are going to look like, I'm going to zoom in a little bit here so you can see my illustration. What our washers are going to look like as a cross section is this. Something like or actually, this is going to be like I drew that poorly, I'm sorry. It's going to be like that, and this will be our outside. I know it's kind of like a weird walnut looking shape because I drew it poorly. That line shouldn't be on the inside. But we're basically going to be finding the volume. This is 2014 question 2. It's a solids of revolution thing. I call it the washer method. I'm not sure if that's like a ubiquitous term or whatever. But we're basically going to be finding the volumes of these washers. So to bring that back out into math terms, going to our formula, we know that the formula of one single slice of our washer is going to be pi big R squared minus pi little r squared, all of that times our change in x. Basically, like, it's the large disk minus the small disk inside. This is 2014 question 2. Calm down. So yeah, you subtract the inner integral from the outer integral. So what we're going to do is take this, and it's going to become this lower region here, wherever we are, is going to be equal to this 2 to get down to y equals -2 plus f of x. The larger radius on the outside no matter where we are in this revolution, we could be over here, we could be over here, it's going to be 6, regardless of our location. So, just to sort of put that into math, we're going to be integrating from 0 to, well, we know this is 0. We have to figure out what this intersection is. Is that given to us? Where's the problem? Okay, that's not given to us, so we need to solve for that. I feel like that's not going to be bad. We're finding the volume of the solid, so we need to also figure out what this is. Does anybody know what that is right off the bat? It's going to be something 4. I'll go punch it into a calculator. Okay, so yeah, x equals 2.3. Thank you, Intense. Or thank you, Teehee. You got to it first. Yeah, so this is going to be 2.34. So we're going to be integrating from 0 to 2.3 this. What that's going to look like, we can bring the pi out to the outside. This is going to be the outer radius squared minus the inner radius squared. We found that the outer radius squared, no matter where we are, because it's a distance of 6 from here to here, is always going to be 36. And our interior radius, if I could speak, is going to be 2 plus this garbage all squared dx. So all that needs to happen from there, you just need to punch that into a calculator, and I don't want to do that. Let me find out what that is. Yeah, dude, you see the name of the video? It's Till We're Done. 7 o'clock to till we're done. Fuck, I've been streaming for 5 hours. God, love me some calc. The 36, this is the big radius squared. That's this distance of 6 from y equals 4 up here to y equals -2. That distance is 6. So no matter where we are revolving our solid around y equals -2, the large radius is going to be 6. Hold on. I'm just going to find the scoring guidelines for this because I don't feel like punching that into a calculator right now. What the hell? Oh, I'm looking at CalcAB. I freaked out for a second. I was like, why are these questions different? It's 2 plus the function for small r because we're revolving around y equals -2. That means that we have to go from the axis up to the function. That's what f of x is. And then to that, we have to add the extra 2 to get down to that thing that we're revolving around. Does that make sense, Intense? If you were revolving around y equals 1, I just want to find scoring guidelines for this. Kiara, the 36 came from the large radius. since our function, I should just put the problem back up so everybody can see it. It's kind of hard to, okay. That should be better. Okay, we're just starting with that, actually. I am real quick gonna run to the bathroom. I will be right back. Yo, I'm back. Okay. All right. What's today? Today's Wednesday? Today is Tuesday. I haven't slept since... Wow. Ooh. This is good stuff. I found the intersection without graphing by using the magic of the calculator. The calculator does a real good job of telling you the answer. That is an interesting analogy, Matt G. I don't think shell is on the test at all. But if you really want me to go over it, I can go over it quickly. Because I think I know how to, like... Ooh, let's just see. I'll look at that donation thing. Ooh, yeah! Yeah, I got it. Thank you. Thank you, August James D. Or however you want me to pronounce your name. Super cool. Okay. So... Okay, this is still not... I'm losing my mind. Okay. Yeah, so 98. Cool. So that's going to be our final answer for this. Next we're going to assume that the region is the base of a solid, and the cross sections are isosceles triangles with a leg. Isosceles right triangles with a leg in R. Okay, so what that's going to look like, I'm going to try and draw that in 3D, just so you can sort of get an idea of what each piece looks like. So, this is going to look weird from your angle, probably. How can I? Okay. So this is the idea. Did it say what they were perpendicular to? Okay. The cross sections are perpendicular to the x-axis. Okay. So what that's going to look like is this. I'm going to let these be the axes. I'm going to plot my graph in light blue. So this is going to be our y equals 4. And our curve is going to look something like this. Now what our cross sections are going to look like? Oh yeah, I should label my axes. Thank you. This will be y. Okay. So, kind of got that piano looking shape. Now this is what our cross sections are going to look like. Because they're isosceles right triangles, that just means a 45, 45, 90. We've got this shape going on. A bunch of these shapes, all perpendicular to that bottom axis. remember the special quality of these is that they're basically it says in the problem that one leg is in R, is in this region. So when I draw this line, I'm going to draw this one a little bit bigger. It's saying that our cross section, it's going to look something like this, basically. This distance this is going to be one slice of our cross section, just how when we were doing shell, or just like when we were doing the washer method, we saw that we were cutting slices. We're also cutting slices when we do cross sections. That's kind of like the definition of a cross section, right? So this little like triangular piece here, this has a width. This little tiny width back here that you can't really see, I'm going to start diagramming in green. This little tiny width, actually I'll bring it up front here. This distance right here that you can barely see, that's going to be our delta x. I should write that a little bigger. Delta x. How can I get my, I'll show the, actually I can probably get it on there with the, so we have that. This distance here, since this line is y equals 4, and this is our, this curve here is following our function f. This distance here, from 4 down to our line, which is going to look kind of like, if I can just do a quick sketch here. It's basically this distance. That's going to be here. This will be 4 minus f of x. And then the area of this triangle, if you remember your, since these two things are the same, since this is an isosceles triangle, the area of this triangle is going to be 1/2 base times height. So base times height is going to be this squared over 2 times 1/2. This is definitely, this is AB. Hey, you got it, Roshan. Good night. So the area of this triangle, or I should say the volume of each cross section is going to equal 1/2 base times height, but since they're the same thing, we're just going to do 4 minus f of x squared delta x. That's going to be the size of that triangular cross-section thing that I drew right there. Just because the base and the height are the same size, the area of this triangle, it's like that times its width. So what that will give us as an integral using that, since we're still integrating from 0 up to 2.3, this is just going to be our function instead. So what we're going to have is the integral from 0 to 2.3 of 1/2 4 minus f of x squared dx. Then you're just going to go punch that into a calculator. Oh, f of x is the garbage function thing that we had before. The formula is not necessarily good for every question. Okay, so where the I took this 2D graph and sort of like flattened it out to show you exactly how the cross sections are being propped up from it. So this distance here, if I just were to like look at this graph normally, like here, let me just look at this graph. This distance here, this is 4. This distance here is f of x. Therefore, the distance, or like the length of the leg that's still inside of R, this green region, for any point inside of the green region, is going to be 4 minus f of x. I can do that if you guys want me to do that one series problem right now, since I have it literally right in front of me, I can do it. If you want me to do it before you guys dip, I have it right here. Should I knock that out real quick? Yeah, you got it, Megan. I've kind of covered this as much as I could. This is I don't really know how to explain it better than I did with this picture. This picture sums it up as much as I possibly can. The volume of this solid is 1/2 4 minus fx squared. I'm just going to scan this and put it in the thing and include the name of the problem. This is 2014. I'm going to scan it, put it in the drive, and then do the series question, okay? Alright. No, it's not the slope. It has nothing to do with the slope. Okay, part C is actually super quick to explain with this, so I'm just going to do that real fast. It just says that a vertical line... Okay, the very last thing I want to talk about with this problem, just because this, like, I can explain it really easily. These are our axes. This is our graph. It says there's a vertical line somewhere that divides it into 2 equal areas. So like something like this, maybe. To find what this is, we're asked to find what this k value is, or we're not asked to find it. We're asked to come up with an equation for it. Basically, we're integrating this area. We want the integral. We want this region to equal this region. So what that's going to look like, if this is 0, and this here is 2.3, then we know that the integral from 0 to k of 4 minus f of x dx, that integral, which represents the area of this region, is going to equal the integral from k to 2.3 of 4 minus f of x. And that's about as separation of variables was one of the very first things I did, Jarrell. If you go to click on the link that's in the description of this video, and you'll be able to go to the you'll be able to see the other part of it. So this is part C. Okay, I'm just going to upload this so I can get to the series problem, so that these people that need to go to bed to sleep well for their exam can do that. This will be up on the drive momentarily. If you don't know what the drive is, every single thing that I'm doing right now, I'm scanning and putting up on Google Drive at that link at the bottom of the screen that you see right now. So all you have to do is go to that link in your browser, and you will be able to look at all the problems that I've done so far. The hit unknown, are you East Coast? Or are you further west? Because if you're further west, I can continue to stay up. I still have 120 people watching this, so I'll do it until there's like 5 left, or nobody's like responding in chat. I will be here, for sure. Been here since there were like 19 people, so. This is cool. I've never tutored this many people before. Sounds good, Smitty. Or whatever your real name is. I doubt your last name is actually Werben Jagerman Jensen. Alright. Yep. Good luck, dude. Yes, series is coming. I hope you're excited. I hope you're happy. It's series time. Bam. Alright, I'm going to save this. This is Solids of Revolution. Yo, thanks for all the subs, everybody. And the Reddit gold and the PayPal donations. It's super cool. Yes, you do, AA Nation. We're about to do it right now. We're going to do a Lagrange problem, like, literally right now. Yo, look at all these subs! Damn. Thank you. Cool. Alright. Let's do some series problems. I love series. That's not true. I'm actually not the biggest fan of series. I don't know if you could tell by my procrastination earlier. Wink, wink. But we're going to make this one happen. Alright. Yo, more subs. Sounds good, Anjesh. Yeah, anybody that is confused, this is going to be BC. If you are AB, don't freak out right now. It's going to be okay. Alright. So we are about to do this. Yeah, that's true, Intense. You got it. That's really the only way to go. Okay, so are we ready? Are we ready for series? I don't think I'm ready. But I'm going to do it anyways. Cool, so let's do this. Man, everybody's talking about this C9 in chat. Savell, I think I'm going to do... Oh, wait, hold on. I got to update my to-do. What I'm going to do right now, here's my plan. I'm going to start going on this coffee. I'm going to do the other half of series right now, and then probably be done with series. Then I will do related rates, and then I will do polar. So whether you want to sleep and come back for that, it's kind of up to you. I don't know what your sleep schedule is, what you're used to. Up to you. Yeah. Okay. Man, I must be so tired. I just looked at the front of the Calc BC exam, and it's like something third-party copyrights contained herein, and I looked at that, and I read third-party copyrights contained heroin. I'm pretty sure there's not heroin inside of the AP exam. Though I figure some kids would probably benefit. Anyway. Alright. Let's do this. So, let f be this garbage function here, and we'll let p of x be the third degree Taylor polynomial. So we're going to have to find that third degree Taylor polynomial, and that's just going to suck ass, but we're going to do it. Okay, so when you're doing excuse me, we're going to take the derivatives about 0. So that's going to be important. We're going to need to know, in order to find we're about to do Taylor series, that one guy, so I don't know what that means, but okay. Yeah, I'm pretty tired, Vind. I did not sleep a wink last night. I was up fucking like all night playing Roller Coaster Tycoon, or just wasted every single minute of sleep that was possible. But oh well. Alright, so we are going to do this problem. Alright, so we're going to need to know f at 0, f prime at 0, f double prime at 0, and, surprisingly, f triple prime at 0. And this is because we have to come up with a third degree Taylor polynomial for f about x equals 0. So we're going to need to know the value of the function and its three derivatives at x equals 0. So this is going to be pretty straightforward. We're going to have this is going to be sine of pi fourths. Next we're going to have 5 cosine pi fourths. Next we'll have negative 25 cosine pi fourths. I'm hoping not losing anybody here. This will be negative 125. Oh my gosh. Here we go. This is going to be sine, because I'm a goofball. This one will be cosine again, that wraps around. Cool. So, just kind of like evaluating each of these by themselves. Yeah. We're immediately, I just immediately evaluated the derivative. If you want me to actually take all the derivatives, I can show you what that looks like over here. You'll have sine of 5x plus pi fourths. So these are all the I'm just taking the derivative each time. It's just chain rule. So this is f, this is f prime, this is f double prime, triple prime, quadruple prime, if you will, or just f4, if you like it like that. Cool, so evaluating each of these, we're going to have root 2 over 2, 5 root 2 over 2, negative 25 root 2 over 2. Can you imagine that? This is going absolutely crazy right now. Negative 125 root 2 over 2. Alright, cool. Yeah. So now that we have these, we can plug into our actual Taylor formula, which I'm hoping you guys remember we're going up to 3 because this is a third degree Taylor polynomial. We're going to do wow, this is sad. This is very sad. It's an A, right? It's definitely an A. I just did this. I'm supposed to be teaching this. Yeah, it's A. Damn right it's A. It's just late. Excuse me, please. Over A over n factorial times x minus A all to the n. So we're going to be doing that from 0 to 3. So what that's going to look like, once we plug all this garbage in up here, it's going to look like root 2 over 2 plus 5 root 2 over 2 times x, because it's going to be x minus 0. So all of these are just going to be x squared, x cubed, x to the 4th, etc. Next we'll have minus 25 root 2 over, but see now, here we had 0 factorial, here we had 1 factorial. So we're going to make this one 2 times 2 factorial, or 4. X squared. Next we'll have minus 125 root 2 over, so we know there's going to be a 2 down here, and also a 3 factorial, so that'll be 12. X cubed. So this is our third degree Taylor polynomial, and it is, as they say, yucko. But also, that's going to equal the p of x that was defined. This is 2004 BC, number 6. Yeah. So next we're asked to find, oh my gosh, that's weird, the coefficient of x to the 22. So we can kind of actually see a pattern here. When we were looking at these, the first derivative was 5 to the first, the second derivative was 5 to the second, the third derivative was 5 to the third, etc. So all we need to figure out is whether or not it's positive or negative, because we know for a fact, just based on the format of the Taylor polynomial, we know that it's going to be, we're going to figure out the sign in a second, 5 to the 22 root 2 over 2 times 22 factorial. And it's just asking for the coefficient, so we're not going to include the x to the 22. But the signs don't alternate because notice the way that you take the signs when you're doing trig is it goes like, yes, August James, I'm going to do that. If you look right here, related rates and optimization are actually up next in our list of things to do. So so the signs alternate, but it's not like on, off, on, off, on, off. What they do, we saw our first derivative was yeah, in terms of the Taylor series, or in terms of the Taylor series, it's always going to be positive. But in this case, we are going to figure out whether or not it's positive or negative based on the way that sine and cosine, their signs alternate when you take their derivatives. Because you see, just based on like what I was doing up here, it went positive, positive, negative, negative, positive, positive, negative, negative, which is a pattern. Your first derivative is going to be positive. Second and third are going to be negative. Fourth is going to be positive. So you have this repeating pattern where on every multiple of 4, you have the last positive. Yeah. So we know 20 is going to be positive. We know 21 is going to be positive. So therefore we know 22 is going to be negative because we're going to follow that sine, cosine, negative cosine pattern. So this is going to be negative. And that'll be that. Yeah, true. All right, cool. So that tells us part B pretty simply. So now part C. Love me some Lagrange error bound. All right. So this is what we're here for. Hold on, I'm gonna chug a thing of coffee before I get in on this. Sorry if you guys can hear me drinking. That's probably disgusting. Okay. I mean, yeah. Man, Macaulay, your name is unfortunately close to McLaurin. Okay. So, yeah, I'm a high school senior. I'm graduating in a couple, like 2 weeks. Yeah, damn. Okay. Okay. So, oh shit. Oh, okay. I saw my little indicator light go red. I thought I was about to drop again. Okay. So now, we are going to use the lovely Lagrange error bound formula. Excuse me. I'm definitely. I'm just going to a state school, but it's on a full. I'm going to a state school because I'm getting paid for it, and I'm going to be on their programming team, which is like they go to Worlds every year, so I'm hoping to go to Worlds for programming. That'd be cool. The ICPC. That's my big dream. Yeah, on national merit. The school's not actually giving me a full ride, but I have the, thing. So that's neat. I'm gonna finish the problem. Nah, it's UCF. I'm a scrub, but UCF's programming team. That's where it's at. Okay. Anyways, I'm gonna just knock this out. I have not gone over particle acceleration. I will do that after I do related rates and optimization and polar and all this other garbage. If you're still awake. Okay, so I am going to solve this problem right now. So, what are we given? Okay, so if you remember that formula that I wrote down earlier, where you take the function minus the approximation absolute value, and then you find what the largest. Here, hold on, I have to write the. Basically, what we're going to do, we're approximating at. Okay, they already tell you. So we're basically verifying that our estimation is within 0.01. Oh, you guys can't see the problem. Never mind. I'm a goon. Yo, just August. Just email me. My email's on the. You can just go to the. Hold on. I'm gonna just put my email in here. Or I probably shouldn't do that. I don't know. There's probably some whack jobs in here. Can you message someone on YouTube? I don't know how that works. It's just because I'm so tired, I'm totally going to forget to email. Yeah, just PM me on Reddit. That's good, August. That's fine. Well, UCF has like a high school programming competition thing that I won, but they compete in the ICPC, which is the International Collegiate Programming Competition, and I'm hoping to qualify for their team. Like I know the coaches and things there, and I'm probably going to be. I know I'm going to be on their team. Whether or not I make Worlds, that's a different story. But I'm going to finish this problem right now. So, the formula that we're going to use for this, we have this. We're just showing basically that our estimation is within 0.01 of the actual value. just going to plug in to that formula that I wrote down earlier, and I think I still have that written down. Yeah. Here we are. Basically, it's this f of n plus 1 of x, the next derivative of x, times, it's just going to be this formula. I'll keep it here while I write down what I'm doing down here in the bottom of the screen. We are basically verifying that this is, excuse me. Yeah, calm down, car. Everybody's getting so, like, heated at me for not doing the shit that they want to see. Just calm down. Be patient or go to bed, whatever you want. Go to Khan Academy if it suits your fancy. Anyways, we're basically going to be looking at... Wait, hold on, did they give us any information? Oh yeah, so we're looking at the fourth derivative, which we found up here earlier. That was 625 sine 5x plus pi over 4. So again, we have to decide whether our maximum value here is at here. I'll do this part in pink again. So we have to decide whether our max is at 0. We're gonna decide if our max is at 0 or 1/10. If we just plug that, if we plug 0 and 1/10 into here, we can see that it's at. So what we're gonna write is this. Using that, can you still see that formula here? Okay, so we're going to write 625 because we found that that was our max on that interval from 0 to 1. You guys can't see what I'm writing down there, can you? Oh, this is so annoying. Okay, that's the best it's going to get. We found that 625 was the max on this interval. So what we're going to do is say 625 times 1 over, or it's just going to be the absolute value we're going to take that to the 4th power because we're working on our 3rd degree Taylor polynomial. So this is the inequality that we have to prove. We're just going to punch this into our calculator and see that it's equal to, I'm not dead, shut up. No, I love calc. Calc's the best. Okay. So when we punch that into a calculator, we get 625 over 4 factorial. Oh man. Nah, that's good. I'm alive. That's going to be 0.0026. And this is definitely less than 1 over 100. So we have proved our Lagrange. We did the Lagrange error bound thing. All right. How do we feel about that? This is just using that formula again that I'll write on here. We're basically plugging it in. I'm not sure what you mean, AA Nation, or double A Nation, or whatever. So I think the last thing we have to do here is part D, which is the easy part, which is coming up with a third degree Taylor polynomial for that integral. This is the easy part. Hey, you got it, Shauna, or Shana, or whatever. So, I wish I had enough space on the damn screen so you could see all this stuff at once. You know what? I can just flip the page over. That's a genius move right there. Genius move by Jacob. Okay. So for part D. Hey, you got it, Simraj. Good night. Okay. So for part D, we're going to follow that same exact Taylor polynomial formula that we've been using for every single series thing that we've done. We're just going to punch it. We're going to take the integral. We can either do them all separately if we want to. That's not exactly necessary. We can just do, I guess I'll write them separately just so you can kind of see how that would work. So we know that if we're doing our nth derivative, we're basically just going from 0 to x. For our first term, we're going to put that root 2 over 2 that we found earlier in there, dt. And that's all going to be plus 0 to the x. For the next term, which will be 5 root 2 over 2 times t dt. And again plus, or I guess, yeah, plus 0 to the x. And then here we're going to bring in that negative 25 root 2 over 2 dt. And that will be the third, that's the third degree, because our first one's not going to matter. So that's good, and then you can just evaluate that. Which actually, it might help to put it all into one integral first, but I'm just going to glaze over that step and say that we're going to have root 2 over 2 t plus, I guess that'll be 5 root 2 over 4 t squared plus negative 25 root 2 over... Oh, did I goof this? I think I goofed this. That has to be over 4. My bad. And I forgot my t squared. What am I doing? Sorry if anybody's still paying attention. Yeah, t squared. Thank you, Stephen. Ah! That's smeared so bad. And it should be over 4 too. Man, I goofed bad. Anyways, so that's going to be over 12 t cubed. And this entire thing is going to be evaluated from 0 to x. But we don't really care about the 0. So we're just going to replace all of this, and we're going to say that our third degree Taylor polynomial is just going to equal root 2 over 2x plus 5 root 2 over 4. Oh, not t. X squared minus 25 root 2 over 12 x cubed. And that's going to be some high quality trash, but it will be the answer to that problem. Alright. What do we think? Do you need me to go over anything else in this problem more in depth, or? Hey, thank you, Simraj. If you're still here, thank you for the money. Alright. Cool. Yeah. And so we know that after we integrate it, we're going to get that x to the third. Alright, yep, related rates are up next. I'm going to scan this and put it in real quick, and we'll be good. I'll just include the problem with this one, that'll be fine. Good night, Steven. Thanks for being here. Oh man, another $5. You guys are great. I'll be here. I don't think I'm going to school tomorrow. I'll probably just chill. Take a fat nap. This has been 6 hours of calc. That's nuts. Wow. Hey. Hey, you know it, dude. Maybe I'm weird. This is fun for me, though. I don't know. man, you say you think about like, oh man, crazy 6 hours, but then you're like, you go to school and your teachers teach for 6 hours every single day. But they don't have the luxury of like jumping between topics. They have to teach the same shit again and again and again to people that don't know it. I don't know. I don't know if I'd be a professor. I definitely want to be a TA in college though. If I can find a class that I like know a little bit about, that'd be cool. I'd rather be working in the industry doing computer science of some sort somewhere. I don't know. Maybe I'll be a professor when I retire. That'd be cool. Hey, good night, Macaulay. Thank you. Alright, Taylor and Lagrange 2 has been posted to the drive for anybody that's still looking there. I'm not sure exactly what industry. All I know is I want to do computer science, but that's not exactly like specific enough to really narrow down a career. That's why I'm going to college, to figure out exactly what I want to do. Let's check out my stream analytics. I'm curious. "96 people watching right now. Neato." Mohan's still awake. Okay, what do you guys want to see? I'll do a problem, if you guys are interested. Alright. No, I don't have a motive, Emily Tay. I'm just into it. I just like this. This is just what I do. Alright. So, looks like we're gonna do related rates. I feel like people are just, you guys want related rates or something. I'll do that. Whoa, why does it say I'm offline? Is my stream online? Ah. Okay, yeah, we're good. No, I don't need a motive. I'm just that dude. Cool. Thank you. Appreciate it. Alright, I just finished off that coffee. Let's do a little bit of related rates. Okay, so I'm gonna find a related rates problem. No, I took this AP exam already. Okay, So I'm gonna fix my to-do real quick. Okay, what am I gonna do? What am I gonna do for related rates? Related rates is definitely, oh, it's parametric. Hey, that's me, Adi. I'm an East Coaster though. Okay, thank you. Double A Nation. I will find that problem and I will do it. Double A, 2011 Form B. I don't know if you're talking about. When you say 2011 Form B, do you mean Calc BC or AB? Oh, it's the same on both of them. Okay, yeah, that's a. No, yeah, no, they're the same problem on. It's the same problem on both tests. It's one of the shared free responses. Okay, yeah, cool. I'll do that real quick. Oh wait. Yes, this is related rates. Okay. All right, I'm alive now. I've been chilling a little. Let's do some stuff. Okay. So, oh, I should probably print this. I'm a genius. Yeah, I'll do my best to explain that. Oh, thank you, Yuno. You're a champ. But I wonder if you read through. Hi. Okay. I'm gonna talk my way through the setup as much as I possibly can. Okay, so this is the problem we have. Because there's so many words here, it would probably be beneficial if you guys just pulled this up yourselves, and I'll just explain it here. No. It's not we're done since 7 p.m. It was 7 p.m. until we're done. That was the idea. But it was originally going to end at 12:30, but that didn't turn out super hot. Okay, so I'm going to explain. Just for reference, I'll put the problem here. We're going to say this is 2011 question 1. Okay. All right. So the first question, I want to know. Okay, so we have cylindrical can of radius. I'm just going to talk my way through this problem as much as I can, double A Nation, just to sort of like help you through where my mind's at. So a cylindrical can of radius 10 millimeters is measuring rainfall. It's initially empty, and rain enters the can over 60 days. The height of the water can be modeled by a function s. the rate at which the height of the water is rising in the can is given by that derivative. Okay, so Cameron, everything that you see on the screen under done, I've already covered. A lot of this stuff, most of the things that I've done, actually every single thing that I've done has been an FRQ of some sort. You can watch this video and kind of rewind, or you can click more, or like you can click into the description and there's a link to another video that has a bunch of other stuff. It's also on my channel, the other AP Calc review video. You can go there to, watch all the old stuff. Did I upload that? Yeah, I did. Okay, cool. So there's a super useful concept that calculus provides, where you get basically the integral. Yeah, trig sub is only BC. The integral of the rate at which something happens with respect to time is going to tell you, or like from A to B, is going to tell you I'm going to put displacement in quotes. This is like a really neat thing that will help if you're doing things involving like particle velocity to displacement or acceleration to velocity or whatever. This tells you how much a function's antiderivative changed over an interval. So things like this question, where you're given the derivative, you're given s prime, and it wants you to tell what the height of the water in the can is after 60 days. Well, we know that the can starts out empty. So we're going to start out with absolutely nothing. And then we're going to add the displacement, or the difference in the height of the water between day 0 and day 60. So we're going to be integrating our derivative, s prime, at t, with respect to t. From here, it's just going to be a matter of like punching in the actual value of s prime. If anybody's like just getting here and wondering what problem we're doing the 2011 problem 1. It's about related rates. So that's the logic here. This you have to keep this in your head. The integral of the rate is going to give you the displacement over that interval. So this, and I'm just looking at the scoring guidelines, so I don't have to go punch this into a calculator so I can move this along, is just going to be 171.813 millimeters. Yeah. This problem was on both the A, B, and BC tests, so you will need to know it regardless of what test you're taking. Okay. So that's cool. That is a super useful trick. Integrate the rate to get displacement. Cool. So now that we have that under our belt, a ton of people, I'm raging, dude. So that's problem A. For B, we want to know what the average rate of change is over that interval. This is a super simple one too. For average rate of change, it's just final minus initial over the length of the interval. That's the thing I'll put up here too. Final minus initial over the interval length. So like what we're going to do here is find how much water we had at the end minus how much water we had to begin with, or I should say the height of the water, and divide that by 60, which is the number of days that have passed. So we just found this number out up here. So we're basically just going to be, this is just going to equal 171.813 over 60, or 2.863 millimeters per day. So that's going to be a simple thing. All right, now we're on to problem C. Double A Nation, are you getting this? Are you cool with me sort of like... Oh, sorry. I have to... This is Form B. I should mention that this is Form B on Jesh. Sorry for the confusion. Okay, so that's the easy part. So now we're going to get to the actual, I guess the related rates when it comes in later. Okay, so assuming no evaporation occurs, at what rate is the volume changing in the can? Okay, so now we're wondering, at what rate does the volume in the can change? So we're given a function to model the height. We know that in relation to the volume of water in the can, or that is the volume of a cylinder, is pi r squared h, right? So pi r squared h. We're given a function that tells us how h changes. So what we're going to want to do is relate the volume to the height. We're going to need to come up with basically a derivative of the volume. So we know the radius. That's everything's done in millimeters, so we can just say this is going to equal 100 pi Does that make sense? Our function that tells us the volume at time t is going to be equal to 100 pi, because that's pi r squared, because the radius doesn't change, times the height at time t. We on board with that? All right, cool. So now when we take this derivative, the only thing that we're doing, like we can say basically v prime at t is going to equal this coefficient times the derivative here. We're going to keep that constant there like we always do, and we're just going to plug in the derivative for t, because that tells us, or the derivative for the height, because that tells us how the height is changing. So all we're asked to do is find how, at what rate the volume is changing at time equals 7. So we're just going to basically plug in v prime at 7, which will be 100 pi times the derivative at 7, which is going to be this garbage. All right, that cool? So now we're going to explain part D. Javera 2, the person that just showed up, are you in Calc AB or Calc BC? Because I can tell you which part I think was the most useful, based on what thing you're taking, what would be the most beneficial. Yeah, related rates are pretty important. Okay, so here we go. We'll look at part D. Parts of A, B that you should know. Make sure you remember how to do all your solids of revolution stuff. Assuming you have series down pat. Series was like the most hotly demanded subject out of everything I did. So if you're not comfortable with that, you should definitely take a look. All the problems that I did on this stream, I've like scanned them and uploaded them to Google Drive. You can get to them at that link at the bottom of the screen, the jmag.me/calc-review. That will show you every single problem that I've done, and you can relate those to the... No, I'm not taking the test. I took the test already. Okay, so part D. Apply the intermediate value theorem. Okay, basically, for part D, if you're looking at part D right now, D at t equals m prime at t minus s prime at t. Basically, you just have to justify that d at t has a zero. Applying the intermediate value theorem, yo, dude, I'm so ready, Leon. Alright, so basically, we're going to look at, since we're given this interval d like 0 to 60, we're going to look at what d0 is, and we're going to look at what d60 is. D0, if you just go plug that into a calculator, because this is totally a calculator problem, if you go plug that into your calculator, you will get negative 0.675. If you plug d at 60 into your calculator, you will get 69.377. So now, what it's asking, we know that because d at t equals m prime at t minus s prime at t, if this equals 0, that means these two are equal. So basically, if d of t has a 0 anywhere on that interval, then we know that somewhere between days 0 and 60, these two functions have the same value at t. Because it crosses from 0 to 60, and because the function is continuous along that entire interval, then we know that there exists a time when they're the same. So basically you can just say Alright, I know that's kind of a sloppy answer, but basically, we know that it's continuous from 0 to 60. We know that it has to cross 0 somewhere between 0 and 60, basically by logic, but you can flesh it out more in that answer. All right, Double A Nation. Yes, that's correct. You know that you can show that the function is continuous and differentiable. I think it's given somewhere. I think probably. Yeah, they're polynomials. They're all continuous functions. It's a trig function that's continuous. It's a polynomial that's continuous because it's continuous on that interval. This is due to the intermediate value theorem. All right, that cool. I kind of want to do a more complicated related rates problem. I have sort of I'll throw together a quick related rates thing just to include with this. The mean value theorem is a different thing entirely. Hey, thanks, Ken. The mean value theorem is talking about slopes of tangent lines. This is strictly talking about a value. Yeah, thank you, Long. Okay, I'm going to do a quick related rates problem. So I'm going to say we have a Yes, true, Garrett. Very, 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 very important. Nah, I can just make this shit up. I just made that problem up. It's related rates problems are really easy to just invent on the spot. Yeah, okay, cool. So if you can read that, we'll just knock it out real quick. No guarantees that it's going to have a pretty answer. Basically, it really helps to draw a picture with these sorts of things. I'm just going to give it a little, do a little art. we're given that this is 8 meters. And this is 2 meters. All right, so this is the center of our cone. So we know that our cone is being filled at a rate of a quarter cubic, 0.25 cubic meters per second. All right. All right, so the volume, I'm going to use a different color. I'm going to use pink. Excuse me. So the volume of this entire cone, but just the volume of a cone is 1/3 pi r squared height. So we know that these are constant. So the current depth of the water, that is like this, like when we're filling, we're basically, what we're wondering, what the question's asking, is how quickly the height is changing with respect to time when we're at this instant that the water is 6 meters deep. Yeah, you should know things like volume of a cone, volume of a sphere. Those I mean, I don't know if you've ever been in a math class, but it'd probably be a useful tool. So what we can come up with here, because we need to kill one of these variables. We need to get rid of since we're going to be looking for the rate at which the height is changing, we need to get rid of this radius variable. We can't have that in here. Or right? Yeah. Because the radius is not going to be constant as we fill it up. So yes, you got it. Brandon's killing it right now. Okay. So yeah. Basically, we can just look at the whole big cone and we can see, oh, check this out. Check out how useful this is. Yeah, we need to kill one of the variables. We can see just by looking at this picture that our radius is 1/4 of our height. And so literally what you can do, you can just take that and just toss that shit right into the R. So we can fill that in. We're going to say our volume is equal to 1/3 pi. We're going to replace R with 1/4 h squared times h. And then we can simplify that and make that a little nicer. That 1/4 will come out to be a 1/16, which will combine with that 1/3 to be 1/48. 1/48 pi h cubed. So now, yeah, I have a feeling Brandon's about to get very excited. We're going to take the derivative of both sides with respect to time. This side is going to become dv dt. So that's cool. That proportion stays constant. I don't know, it does. It's not gonna like, oh, because it's like, here, I can explain why the proportion stays constant. I'm gonna take a quick sidebar. Actually, this is small enough to do on an index card. Basically, when you think about the cross section of a cone, like just straight down the center, it's just an isosceles triangle. So this here, as the water like comes down here, these triangles are similar. So the proportions are going to be the same no matter where you are in the triangle. Isn't that super neat? Isn't that some cool sauce? Yeah, you got some similar triangles going on inside this cone. So no matter where you are, the proportion is going to stay constant, which is what allows us to just say, okay, our radius is going to be a quarter of our height no matter where we are, because that's how cones work. Isn't that sick? Yeah, cool sauce. All right, so now that we know that, we can just finish our, yeah, me too, you know. So just like taking the derivative of this, I'm going to do some power rule garbage. We'll get 3 over 48, which is, what's that, like 1 over 16? And since we're taking the derivative with respect to time, we're going to add that dh dt over here. And guess what? Now we have everything we need because we know the rate at which our volume is changing. We know the height that we're curious about. So all we need to do now is just plug in 1/4, because we have that 0.25, equals 1/16 pi. We're wondering about 6 meters squared dh dt. And now all we got to do is solve for the height. So that's going to be some math. Multiply both sides by 16. 4 over pi. 4 over 36 pi. 1 over 9 pi equals dh dt. Blammo. No, dude, fuck your chain rule. We don't need chain rule. This is power rule. It's just a constant. That's why we change. That's why we change the r to h, because what we end up with here is just we just do power rule on this thing because we have a constant value in front of here, the 1/48 pi. We just do power rule. Bring that down, turns to 1/16 pi. Decrement the. I almost call it an asterisk. That's an exponent. Yeah, that's the answer. 1 over 9 pi. Pretty sure, unless I'm a goofy goober. 4 over 36. That's definitely 1/9. Yeah, 1 over 9 pi. Cool. I'm waiting, yo, Matthew. Fill me in. Uh, 3 over 48 is 1 over 16. Matthew. Man, you're tripping me out, Austin. What happens when you rotate a square? Welcome to Jacob's magical calculus workshop. We're about to rotate a square. Man, intense. You've been missing out. We did some related rates and I blew some minds with some similar triangles. These people are going nuts. Yep, that's correct, Matthew. No, I just wrote a problem. We just did it. It was pretty cool. Came up with it on the fly like a cool guy. Matthew, or wait, who asked the question? Austin. Here we go. Here's the answer to your query. Here we go. We're about to have our minds blown. All right. Cool. So, hold on. Did I do 2 related rates problems? Yeah, I did. Just to show you one more common shape that you'll see in related rates problems. Sometimes you'll see like a triangular prism. Just to show you how to set up a relationship for that. I've seen pictures. Normally they'll give you a picture instead of a. Hey, you got it, Brandon. That's the stuff. Sometimes you'll see a problem that's like posed like this. So for these, if you're given a relationship, like you say, okay, we're going to call this, let's just say this is like 8 meters. This is 4 meters, and this is 20 meters. If you know that the volume is changing, basically you can use all the same concepts of similar triangles here. If you know that the, wait, hold on. Yeah, basically if you need to know how the volume is changing in relationship to the depth of the water, again, like if we're doing something like that where you have the water level coming in somewhere like this. And all this below is filled with water. Then you can say, basically, when the entire tank is full, we know we're going to have length times width times height over, like the volume of this entire thing is 1/2 length times width times height, or the length and the width. Wait, what's that going to be? 320. So, the relationships between everything are going to stay the same. So 20, like, I don't even know what I'm trying to say here. I don't know. Whatever. You get the idea. Similar triangles are a thing everywhere. I don't even know what I'm... Basically, no matter where you are in this, no matter how full it is, because we see this 8, 4, 20 relationship, if this is our length, or no, this is our length, this is our width, and this is our height, no matter where we are, our width is going to be twice our height. Our length is going to be 5 times our height, etc. All these relationships are going to be true no matter where you are. And I love the idea, Ritvik. Okay, so let's, what do we want to do? Someone told me to do an equilateral triangle. Man, who was I supposed to shout out? Like Plegout or something? Like Plegout? Someone told me to do an equilateral triangle, so I'm gonna do that. Here you go. Alright. That's kind of equilateral. Whatever. Alright, what's next? What do you guys want to do? What is a continuity problem where you have to find K, A, B, C? I don't know what that means. Oh, polar shit? No, dude. It's all about the equilateral triangles. Fuck polar. No, we'll do, let's do a polar problem. Well, polar's Calc BC. How many people are... polar or optimization, because I feel like... How many people here are AB versus BC? Like, who needs what? Plugato! I don't know who Plugato is, but... Okay, no, for real, though. Oh my god, this is so... Okay, I'm just gonna... If you have... That's the area of an equilateral triangle given its given one side length. Just write that down. Shove that into your brain, whoever just asked me. Who asked me that? LT. LT. That's gonna be what you want. Put that in your brain. Put that in your brain. Put that in your brain. Okay. So, hey, good night. No, it's all good. That's what I'm here for. I like this. Cool. So let's do a. All right. I guess I'll do a calculator problem. You would really only need to. Brandon, if you send 100, I will absolutely stay up all night. For sure. Payment in advance, though. I promise. Represent. Okay. All right. Here's what we're gonna do. We're gonna do a polar problem. And you guys can chill. Everything on the to-do list is gonna get 2 done. I did not think I'd be up this late, but it's all good. I love you guys. We're doing some shit. I mean, do you need it, Brandon? I feel like you should sleep. Are you taking this exam? You better not cash back, Brandon. I'll fight you. BC is basically AB with series. I don't understand. Polar isn't even, I know for a fact Polar isn't going to be on dumb fucking test, whatever. I just did an AB and BC top, but I can't go from AB to BC because like everything on AB is on BC. It's kind of goofy. All right, someone find me a polar problem and I'll do it. I didn't say polar won't be on there. I don't know if I said that. Dragon Blade, I'm a senior in high school. I don't know why these people think that polar is not going to be on there. Why would polar not be on there? You guys are so confident. What are you so confident for? How do you know? You're talking like you freaking wrote the test. Alright, thank you, Intense. I'll do that. 2014, question 2. I've done a lot of 2014 today. Wild. Alright, I have fucking like 9 quintillion tabs open. I don't know anything about what will or will not be on this exam. Well, geez, AA Nation, if you're so damn passionate about it, find another problem and I'll do it. But please be quick. I want to get to as much as possible. Wow, Brandon, that was very poignant. Very wise. Nah, dude, I hate multiple choice. Yo, everybody go upvote my Reddit post if you haven't already. It's at jmag.me/abc. I'll pop a link in this chat. Please go upvote. I want my Reddit karma. Yo, Brandon, get out of here. Multiple choice. Multiple choice. Got him. Nobody knows if polar will be on there or not. Nobody really knows. We're all just assuming. Nah, Brandon Wee, you're chill. Brandon Lowe is off the fucking walls, dude. I don't even know what's up with him. Holy moly! This exam, my first video has 3,000 views. Why don't I monetize? That's absolutely not true, Brandon. Get out of here. Yo, Double A Nation, where you at with that thing? ...2007. Thank you. Okay, I get you. I got it, dude. I got it. All right, looks like we're gonna do 2007 number 3. Cause your boy Double A Nation came in clutch with that actual. Unauthorized. I'm unauthorized. Just kidding. 2007 number 3. Are we talking about Form A or like the regular form or Form B? I don't know how math works. Yo, like jmag.me/abc. Anybody still studying could use this link. Hit it up. Blow it up, dude. Blow it up. Blow it up. Alright, I'm gonna stop acting like an idiot and do this problem. 2017, number 3. Alright, let me print it out real quick. No way you do it, Brandon. You won't. You won't do it. You won't. No way. No way you do it, dude. I put... No, there's absolutely no way you send me $100. Darn, why am I not at the top of AP students? I feel hated. I don't see the money yet, Brandon. Where are you at? I've been out here for 7 hours and I can't get a damn... Can't even get $100, bro. Jesus, Gerardo. I mean, honestly, it's probably more reasonable. I did stuff pretty slow, so everybody could like have a chance to say that they understood it, or at least pretend that they thought they understood it. Okay, so we're gonna do this problem next. Oh shit. Okay. I'm going nuts, dude. It's getting late. Man, normally when I like private tutor, because I do this occasionally, but most of the time I do private tutoring where I just like everything else. I private tutor $40 an hour. That's my rate. $40 an hour. And what am I doing here? I'm getting the cool zero. I'm getting the cool zero. Nay. $0. No dinero. Yeah, I'll tutor you. I'll tutor you any day of the week for $40 an hour. That's my rate. It's way better. I can solemnly say it's definitely better than $0 an hour for sure. Yeah. Yo, I'll be right back. I gotta hit the bathroom. Wait. I'm bringing the hashtag back. Where'd the square go? Rotate the rectangle or something. I don't know. Rotate the square. Back in a flash. Yo, what up? Okay. Okay. Yo, who's stealing my job? Man, Sonic the Hedgehog. Okay. Let's do this problem real quick. Hashtag. Yeah. Alright. Later, tater. Let's do some calculus. Moo. Love me some calculus. I'm going nuts, so let's just do math. I'm gonna shut up now on the non-math shit. Okay. Yeah, I got beef with Brandon Lowe for not sending me my Honda. Okay. Here we go. So here we go. Part 1. Let R be the region inside of this graph yeah, me too, Mr. Bowden. So here we go. We got that region. We want to know the area of this region. So what we're going to do is we have a circle here, don't we? Yeah, so we can very easily man, I can't even speak. Okay, so we can very easily find out what we're going to do is we're going to split this because we see these intersections, like these points of intersection. Can I blow this up? I can just make it big for you guys. What we're going to do, essentially, oh jeez, that's nuts. Alright, that's good. So what we're going to do is split this right on these points of intersection. This one right here, and this one right here. When I draw these lines in, this is a calculator question. This is actually, I have to answer like Gerardo asked. This is a calculator question. Yeah, you got it, dude. All right, so this basically when I go in like this and I draw these lines, everything inside of this angle is just part of the circle. They tell us the angles at which the curves intersect. This one here, we've got 4 pi thirds. And up here we've got 2 pi thirds. That means that 2/3 of the circle is contained by this angle. This is 240 degrees. So we know this, like we can figure out this, the area of this region that I'm shading in blue. We can figure that shit out instantly. That's just 2/3 of the area of the circle. The only thing that we really have to integrate is going to be this region that the little like butt comes in there. So what we're going to do is we're going to split our like sum representing the region into 2 pieces. So what we'll do for that, for part A, we're looking at right now. How many is this? I want to do it in blue. Alright, so for part A, this region of the circle we can totally figure out. That's going to be 2/3 of our circle, which has an area of pi r squared, and our radius is 2. That's given in the problem. So 2/3 pi 2 squared. So that's this region that I've shaded in blue. Now, for the next half of it, we're going to do our polar integration, which I would just like to take a quick sidebar to actually explain how this works. So, do I want to explain how polar works? Do you guys want to like know conceptually why the formula for polar works, or do you just want me to remind you of the formula for polar? Now I gotta wait like a minute for that message to get to, and a minute for the text to get back to me because chat's so latent. What do you guys want? Yes, I gave you an option. I gave you 2 things. Neither formula. You just want the formula. What? Just say conceptual or formula, or like concept or formula. Okay, I'm going to give the formula part real quick, and then I'll explain the conceptual part. I'll give both. I'm going to give both. So the straight up formula, the straight up polar integration formula. I really like explaining the. Whatever. I'll just give you the formula. So the basically what you're doing is you're integrating from your first angle, which is generally written as alpha, to your second angle beta, 1/2 the radius that you're integrating to squared d theta. That's it. Nothing fancy. That's it. Plain freaking simple. R is the distance away that you're integrating. So like on this picture, within this interval, we're integrating. I'm just going to pull that 1/2 out to the front here. I'm bringing out the one. Chill, Ritvik. You're always going to integrate counterclockwise. You're integrating like you're going to write the angles in ascending order. So basically, I'm going to be integrating from 2 pi thirds to 4 pi thirds because they give the angles of intersection. And I'm just literally going to plug in the r here, which is 3 plus 2 cosine theta. And that's d theta. So that's literally, that's it. There's nothing fancy. There's just this part for the interior, and there's this other part in there. And so you just punch that into your calculator and you get at that super 10.37. That's the answer for part A. Nothing fancy. Really, guys? You don't want to know the conceptual stuff? Well. Yeah, counterclockwise. That'll do you in. You're not going to integrate. Yeah, if you integrate from here to here, you're going to have a bad time. Okay. So now we've got that. That's part A. Fuck conceptual. Rude. Yeah, it's saving me time. It's true. We're gonna get to more stuff. So Brandon Lowe can give me my money, but I think he's dead. I think he's gone. Sent the mob after him because he didn't pay up his $100. All right. So particles moving with a non-zero velocity along the polar curve. Theta equals 0 and t equals, okay. dr dt equals dr d theta. Alright, so basically, yeah, for real. So we're just going to evaluate the derivative, like dr dt and dr d theta. They have to be equal. Or like we know that they are equal. That's literally like, you can just use your calculator for that, because your calculator can calculate the derivative at a point. This is absolutely like nothing. There's nothing fancy about this. You just you just go to your calculator and say dr dt. We want to evaluate that at theta equals pi over 3, and that literally plugging that into your calculator will give you negative 1.732. That's it. And so for the question about whether or not it's moving further away from or like towards the origin, because this is saying like the radius is decreasing with respect to time. They say that dr dt equals dr d theta. If the radius is decreasing as theta increases, you can think of that as it kind of like spiraling into the center. Basically, if as I'm going around this, my radius is decreasing, I'm going to be going closer to the center. So that's that. Yeah, series is B, so you don't need to know series for AB. And lastly, for part C of this, once the value of dy, okay, so dy dt equals dy d theta. Find the value of dy d theta. Theta equals pi or thirds, and interpret this. Okay, so this one will be interesting. Let me think about this. We know y equals r sine theta okay, yeah, so it says dy dt is equal to dy d theta. Oh, okay, so this isn't hard. we're just going to say r sine theta, that's just going to be equal to the radius, yeah, here we go. 3 plus 2 cosine theta, sine theta, by just taking this r and plugging them in right there. So then, once again, yeah, I know. So we're just going to take this and evaluate that again. We're just going to take this is literally a calculator problem. This is just, do you know how to use your calculator to find a derivative? Yeah, this is it. There's nothing fancy about this. Okay, I don't even know if this is like, does anybody have an actual polar question based on this? Yeah, this is just calculator stuff. Really, the most important thing you're going to need to know is that formula. As long as you know that formula, you can probably figure out most of the polar stuff. There's not really anything too tricky about this one. Anybody still stumped on anything relating to this? Or should I move on to an optimization problem? Yeah, I got you. It's no worry. Hey, I just got more Reddit gold. Thank you, whoever that was, if you're still on the stream. Oh, that's 2 hours ago. Never mind. I can't read. Sweet. All right. What are we gonna do? I don't even know if that. Oh shoot! I didn't upload this related rates stuff. Yeah, polar is literally that one formula. I'm gonna upload this related rates thing that I did not upload before. Did I? Shoot! What did I do with that problem? Ah! Okay, here we go. Yeah, we'll do an optimization problem. I'm just going to upload this related rates thing that I didn't upload before. That was a bit of a goof. That was a bit of a goof for sure. I don't even know what Reddit Gold is for. All I know is that it costs money, and then it means something when people give it to you. That's cool. My Reddit karma has, like, everything's doubled overnight. That's neato. We're going to back burner that, Guevara. Jonathan, for Lagrange error, whatever, you can scroll back through basically go through the video, go back until you see series and Lagrange on top of the to-do list. Like, if it's the very top thing, that means I'm currently going over it. You can refer to the work that I've done using the link at the bottom of the screen. You see that jmag.me/calcreview? If you go there, you'll see all of the things that I've done tonight, all of the different problems. I'm actually scanning another one right now and uploading it, so you can go over all the things that I've done. Yeah, no problem. So this was related rates. All right, so all the related rates stuff is now up on the thing if anybody needs to look at it. Damn, I've done this is a lot of pages of stuff. Hey, no problem, Guevara. Alright, so let's have a look at optimization. Double A Nation, would you rather do optimization or polar? Or does anybody else have any input for what they want to do? Yeah, bedtime coming up. Brandon Lowe, thought you were up all night, dude. What a scammer. It's up to you. I'll do whatever. I got all the I got all the coffee in the world. Optimization. Alright, let's hit an optimization problem. You guys can start hunting in the FRQ, see if you can find anything good. I'll look too. We'll do both guitar, or gut, or whatever you are. Whoever you are. I bet I can make up an optimization problem that's hard. I can probably come up with something. Let's, okay. I think I have one. Alright. I think so. Maybe. I don't actually know. I don't know if this is going to be hard or not. Okay. Alright, here's what we'll do. Yeah, I'm doing optimization right now. I'm just kind of gonna like invent a optimization problem and kind of hope it works out. I think it'll be good though. This will be good. I need to come up with a curve though. I'm getting my graphing calculator real quick. Okay, I think I have one. I'm just gonna... Okay. PyCake, if you want to do Taylor and Lagrange stuff, go back through the video. Look for when the things that you want to study are at the top of the to-do list. That means I'm currently going over them, except for polar. I apparently forgot to move things around for polar. I'm going to put that in the done list. For Lagrange, go to the link that's at the bottom of the video, jmag.me/calcreview, and you can see all of the stuff that I've done for it already, like the actual exercises. Okay, so here's the problem that we're going to do. Actually, I feel like this is going to be easy. Actually, it might not be easy. Well, you know what? Whatever. It's optimization. We'll find out if it's easy. So, the question is, we have this curve and it looks pretty terrible, but whatever. And what we want to do is place some quadrilateral of maximal area beneath this parabola. So I'm not going to go through all the super simple algebra stuff where I find like the vertex and the axis, whatever. We're all adults here. We can figure out that this is going to be x equals 8. So now it's just a matter of turning this into an optimization problem. So fair to say that because this is symmetric, we can split it down the center, because whatever rectangle we put in here, it's going to be symmetric with respect to the axis of symmetry of this curve. So we can find our question is going to be the maximal area of this. So if we can change the problem to be what's the maximal rectangle that we can fit just to the left of the axis of symmetry, that is between 0 and 8, then we can just double that when we're done. Does that make sense to you guys? Like basically this is just going to be like, there's just going to be a ghost half of this on the other side. We're just going to solve the optimization on the left side and then double our answer when we're done, because everything's going to be symmetric. So we need to come up with some kind of a function on this interval that's going to tell us what the area of our rectangle is between 0 and 8. So to sort of like talk through my logic of how I would create such a function, I know that the area of my rectangle is going to be equal to this distance. Like as I'm moving across here, it's going to be equal to this distance times this distance, that vertical distance. This up here, this length, is f of x. And this distance here is going to be 8 minus x. So it stands to reason that the area of my rectangle, which I'll call a of x, is going to equal 8 minus x times f of x. We can check that at 0, like there are a couple places where we can kind of like verify that that's correct, and that's at this point and this point. If we plug in 0 for x, then we're going to have a horizontal, like a width of our rectangle of 8 times f of x. F of 0 is going to be 0. We can just kind of tell by looking at it. So that's cool, that works out. Same thing works when we plug in 8 for x. We see this is going to be 0. So we kind of have an idea of how it's going to behave on here. Yes, I will, Anjesh. Yeah, the first half's already public. I'll make this one public the second it's done. So what we're going to do is we're going to take our function, this a of x, and we're going to take its derivative, because the way optimization works is we need to find a 0 for the derivative, because this is a function that tells us what the area of our rectangle is going to be. It's going to have some maximum on that interval, and we're going to figure out what it is, because we know it goes from 0 to 0, and it's increasing as we go from here to here. So by the mean value theorem, there's going to be some maximum that exists along that interval from 0 to 8. So I'm just gonna, I guess I could probably, whatever, I'm just gonna do it by hand. Okay, so EVT? Well, it's just Rolle's theorem. EVT. Am I stupid? Do I not know what the EVT is? What's the EVT? Extreme value theorem. Oh, it's you. Yeah. Oh yeah, you got me. You got me. Yeah, extreme value theorem. I goofed. My bad. Yeah, you know what I mean. So now we have our function a of x that tells us what the area is of our rectangle for some x. So we'll take this derivative. And now we're going to punch this into a, you know what? No, we're going to punch this into our brain power machines and we're going to find out what it is by hand. I have a feeling it's going to be 4. We're going to set that equal to 0, which means we can multiply everything by 8/3. Does that get pretty? That becomes x squared 6 times 8 over 3. And that's 16x. 16? Rational root theorem. And then you're just going to solve that using your noodle. Or you can just use Wolfram Alpha, which is what I'm going to do at this point in time. And it looks like our answer is going to be, wowzers, 8 minus 8 over root 3. And that's going to be our value for x. So that's going to be, oh, you can't see that, can you? Well, yes, that's some shit. That's just our value for x. Now this is what we have to plug back in up here to get our actual area. So this is just going to be 8 minus I don't want to go do that. Let's find out what that Wolfram Alpha to the rescue. Oh man, I got disconnected for a second. it looks like I'm getting something. It's like roughly 24.63, which I then have to multiply by 2 because of all of the junk I was saying at the beginning, which would give me something like, I don't know, 49.26. And that's what we're getting. That's our max. Now I'm going to make sure that Wolfram Alpha agrees with me. Okay, so we all cool with that? Yeah, we're good. That was the max. My answer was right. Sick nasty. Garrett, can you provide a link to that? I'm not sure. What do you mean sample question? There's a lot of questions that College Board provides. Hey. Spaces! Alright, I'm gonna upload this real quick with a little explanation of what the problem is. Alright, AP Calculus sample questions. AP, okay. Alright, I think I found, I assume I know what you're talking about. Garrett, can you tell me if it is, you want BC question 3? I don't know what are you talking about multiple choice? Sample BC question number 3. We talking like, for what value of k, if any, is the integral from 0 to infinity of kx e to the negative 2x that whole garbage? Okay. I'm gonna upload this thing to the paper that everything that I'm writing. I don't know if you yo Vic, it's not 3 o'clock yet. Stay the course. I didn't even do piecewise functions. Hold on. Oh my gosh, I can't believe I actually got through all this. This is nuts. Yo, damn, I'm super proud of tonight. This has been good. This has been good. This feels good. I'm glad there have been more than 1,000 unique people on this stream today. And that is neato. I'm looking at the analytics thing. Yeah, I got you, Isaac. Sleep well. Okay, I'll have a look at this problem right now, Garrett. I'll explain it. Yeah, Double A Nation, that's what's up. Hit me up, jmag.me. Send me that. Just catch me on GitHub. Catch me on PayPal. Yeah, Ritvic's been here. Ritvic's an OG. Hey, absolutely, Isaac. You have a good night. Okay, I'm going to explain this problem real quick, Garrett. I'm pretty sure I'm frozen right now. Oh my gosh, I'm going in and out. Yo, I'm East Coast too, though. But I had a 5-hour. Were you guys here back in the 5-hour energy days? Did you guys see me drink the 5-hour energy? Irazu, no! No, it's okay. It's alright. It's gonna be okay. The test isn't that bad. If you're taking Calc BC, be safe in the knowledge that like more than 50% of people get a 5. Like it is absolutely an obscene percentage of people that do well in this exam. If you have, are you taking Irazu? Are you taking AB or BC? AB? Oh, you guys are still here. I didn't realize there's so many people there. I guess there are 35 people watching. I wonder how many people are watching and just staying silent. Yeah, looks like Piecewise is the last topic. I mean, I don't even know what to do with piecewise functions. Like, what do you guys want to do with piecewise functions? I feel like we kind of, like, I don't know. It's getting to that time of the night where all I want to do is rotate some rectangles. Does somebody still want piecewise functions? Does anybody still care? We've done so much calculus. You guys aren't getting fried yet? Yeah, dude. Rotate the square. Rotate the square. Yo, it's been real. stuff to memorize, know all your, I don't know how to integrate stuff, know how to differentiate stuff. That's good. I hear that's good. If you know how to optimize things, that'll be helpful as well. If you, I don't know, just do the math, basically. Oh, man. Dang, Gary, I almost forgot about you. Hold on. Wait, what? What the heck? $129? What? When did that get 129 comments? What? Do my videos have comments? They don't have that many views. What? Okay. Garrett's question. Alright, for what value of k? Let's see, we're gonna knock out a little improper integral action. Am I blind? I don't know if I can... Hold on a second. Hold up, wait up, hold up, wait up, wait up, wait up, wait up, hold up. Okay, so let's do this. We're going to factor out this constant at the front. We're going to be integrating. It looks like we're going to integrate by parts. I'm not 150% sure how to approach this, but I'm pretty sure I'm just gonna hit it with everything I got this final hour. Hopefully I have the right approach. Sorry to be of uncertainty here, but we're gonna have k times this integral x e to the negative 2x 0 to infinity. I'm gonna do a little bit of integration by parts, I guess. Hour? Who said anything about an hour? I didn't even put a dx. What am I doing? So do you guys know how to take an integral from 0 to infinity and turn it into like a limit? I'm hoping, because when I change this to like the UV, it's going to be the limit as t approaches infinity of like basically this. I'm going to take the UV. I'm going to say negative x over 2 e to negative 2x, because that's my UV. It's the limit of that as it approaches. Like that's how that's gonna look. I know that looks wonky. Does that make sense? Are you guys familiar with this? I'm hoping, maybe. Garrett. Because then after that, it's just the integral. Because you're still gonna have the 0 to infinity of v du. Which when I pull out that negative 1/2 v, yeah. And that we can just evaluate like human beings. Yeah, cool. We're just gonna cool. This part here, as t goes to infinity, let's evaluate this puppy first. This is all supposed to equal 1 when we're done. This guy here, you're gonna have, well, the second term is obviously gonna equal 0, so that's nice. So you're really just plugging in infinity for x here. So you're gonna have something that's gonna look like negative infinity over 2 e to the negative 2x. Basically, as infinity gets like big here, this thing is going to get super small because it's net to the negative 2. So this whole thing is just going to go to the whole thing is just going to go to 0. That just dies. So all you're left with now is k times, I'm going to factor out that 1/2, k over 2 times the integral of e to the negative 2x from 0 to infinity dx. Now that's going to equal 1. Is this working for anybody yet? I'm hoping for, oh, maybe if I focus the freaking camera on my work, it would be good. Okay, so that whole thing goes to 0. So this is good stuff. Now we're going to take this. This is going to become, we're just going to integrate this into the same little limit gig that we did before. X is in the exponent, except it's a negative exponent. So it does that thing where it goes on the bottom and goes to 0 instead, because it's a negative exponent. The x in the exponent is going to infinity, but it's a negative exponent, so it's going to all go to 0. Double animation, it's negative. See that negative right there? Neg. Yeah, so, oh, yeah, we ballin' now. Cool. So now we just got this, and this one I'm hoping will be a little bit easier to solve. So we're going to have, I'm just going to, I hate that 2 over there. We're bringing them over here. So now we have k times the limit. We'll do again as t approaches infinity of this garbage, negative 1 half e to the negative 2x evaluated from 0 to t equals 2. I'm going to pull that negative 1/2 right the heck out in front of this limit, because that's the thing I can do. This is for a b. This is BC. This is an improper integral, so you don't got to worry about this, Mr. Man. So this is just. That's just gonna turn this guy to a 4. That's cool with you guys. I'm just gonna do a little math magic. Okay, so now we have k times the limit as t approaches infinity of e negative 2x 0 to t. So that's going to be, that's when this is infinity. Oh, sorry, that's going to be negative 4. I goofed. Don't forget that negative from the negative 1/2 there. That's all going to be equal to negative 4. We'll see when I bring this whole garbage out to infinity, that's going to be 0. So we're going to have k, for the same reason as the other one. It's also going to be 0, so we're going to have 0 minus e to the 0 equals negative 4. Oh my gosh, I'm going to cry. K times negative 1. Oh, I forgot the 1. K times negative 1 equals negative 4. K equals 4. Oh my gosh. C, it's answer choice. It's answer choice C. I did it. I know that was a lot. That was a lot. I feel like I just kind of, I don't know if I explained that very well. I was just kind of babbling the whole time. What do you think, Garrett? You haven't spoken in a hot minute. I feel like I might have lost people. What are we thinking? Hey, it's my pleasure. I'm probably going to, you know what I'll do? Because I'm going to stay home all day tomorrow. Yeah, damn right I need some sleep. Here's what I'll do. Probably tomorrow I'll make a post on Reddit. You go to, I don't know if you guys came here from Reddit or if you just like stumbled on this on YouTube. But I'm going to make a post on r/AP students. And if you guys want to let me know how the test went for you, that'd be awesome. I'm not taking any tests. I'm a senior. I took all these already. I'm just doing this for fun. Yeah, Reddit. Right now I'm taking discrete math. Well, this year I've taken discrete math and linear algebra, dual enrollment. It's been lit. We never got to piecewise functions, but I don't give a fuck about piecewise functions. We did some improper integrals. I'm going to change my to-do list so it looks like we were... Right. Wasted. Wow, okay. It's been crazy. Discrete math, it's basically like math without numbers. It's kind of like logic. I'm going to UCF, but it's on like a full scholarship. I'm going there for computer science, but I'm going to be doing competitive programming. That's like the real draw for me. All right, well, thank you all for showing up. It feels awesome to have helped out people. I like this. It's been good. I hope you all do super well tomorrow. It'd be awesome if you let me know or something about it. I'm on Reddit, Block in the Sky, or you can email me at jacobmagnuson.com. Yeah, no, absolutely. Yeah, go for the 5. Get the 5. Yeah, my pleasure. Hey, thank you. All right. It's been real. I will, yeah, go for the 6. Get that 6. Get that perfect score. Don't get a single question wrong. Yeah. I've thought about it. I did some for my class this year. Well, like I don't know if you can see like the other stuff on my channel. I did another one of these before my class's discrete final, but that only had like 9 people watching at a time. This one there were like 300 people watching this at one time. That was awesome. Felt it's good stuff. Maybe I'll do some standalone videos. We'll see. It's been fun. I like the interaction though. Maybe I'll make it like a regular thing where I kind of have some like active teaching things. Like I'll make a weekly live stream where I just take math problems and explain them. That'd be neat. Aw, sick, thanks. Yeah, Rick, are you in Florida? Yeah, hit me up. This is what I do. I've been tutoring since anything that I went over today. I'm gonna make this video public. There's a link. You see the link at the bottom of my the link at the bottom of the video where it says jmag.me/calc review. Every single thing that I've done, I've scanned and uploaded to Google Drive. I'll actually drop that link in right now in case you don't know how to type or something. Alright, yeah, good night. Thanks for coming out, everybody. I'll stick around till the viewer count dips. Good luck, everyone. Let me know how you do on Reddit. I really want to know. Good night, dude. Thanks for hanging out. Hey. Good night, good night. Thanks for being here. Good luck to everybody. Hell yeah, Garrett. Sounds good to me. Yo, can I count my 5 though? Just to start us off. Not trying to brag, I just 5 shots. Sweet. Alright. It's all officially up on the drive. We made it. How many topics did we cover? There are 14 things in this folder. We went through 14 different varieties of problems in 7 hours. That's good. Damn. It's like a topic at best. Wow. That's good stuff. Yeah, too many. Alright, I'm out of here. Good night, everybody. I mean, I keep saying good night. I don't actually want to go anywhere. I'm just, you know, I drank so much coffee. I'm not even that tired. You got it, dude. That's a second derivative, Felix. Man, all I want are analytics for that first video. Oh, yo, Red Vic, my man. How many subs did I get? That's the question. Tetris, LT? I can't believe that first video that I did has 3,500 views. I've never like used YouTube before. This is sick. This is good. Definitely 100 duck-sized horses. Easy question. No, dude, we back. Yo, I will, I'll give an advanced copy of the free response questions to anybody that can freaking solve this problem. It's been baffling me today. I need to know how long that line is. I got no clue how long that line is. All I know is that there's that triangle, the 13, 14, 15 thing, and there's a circle in there, and there's a circle out there, and there's I don't know how far away their centers are. I gotta know. I gotta know. I have no idea how to. That's just stupid. Here we go. Here's a tricky one. You guys should go to bed. You have a test. You guys are gonna be like falling asleep in the test, and this whole thing is gonna be for like it's gonna go to shit. If I turn off the live stream, people will leave, but I don't want to turn off the live stream because I'm not tired. What do we do about that? Dude, look at these shoes. My friend's birthday was a couple of days ago, and for his birthday, my girlfriend painted him shoes. I don't know if you guys are familiar with acid rap. There's like it was inspired by an album cover. Here, 1 second. This is this is like the album cover. Just some like hip hop dude, right? You can't really. The colors are so messed up, and I guess it kind of looks good. It looks okay at an angle. So that's the album cover, right? Look at these shoes. She freaking painted these. It doesn't even like. I can't even fathom. Hold on, let me see how to like. I have to flip this off. You can't even see. Hold on. You can't tell. Oh, I guess you. Damn it. I have to turn rotation lock 1 second. Yeah, Chance. It's kind of hard to see. They look so much better in the picture. It's not like going through isn't that sick? Yeah, it's insane. She like sketched it out first, just like on a picture of a shoe. It's nuts. She's insane. Yeah, they're dope. Alright, did someone ask me for volume by rotation? I suppose I could do like a no volume Solids of Revolution was in this video. For some reason I have to like stop it and upload it before you can get to it. So I don't know. I guess I kind of have to do it. You guys should leave. You should sleep. Alright. I think you guys should actually go to bed. Alright. I'm gonna flip off the live stream with a heavy heart. Shout out, who the hell is Plugato? Who is Plugato? Someone, I never got it. Nobody ever filled me in. Nobody ever filled me in. No? Yo, Patrick, chill. Wait, hold on. I gotta do a bit of an art project to finish off the stream. I couldn't find the other square, so I gotta, you know. Vic, were you here when I drank the 5 Hour Energy? Like, were you here? Are you that OG?